audible? Hello,
Yes,
Shumi.
ma'am. Audible.
You are not audible at all. It's
Hello, ma'am.
breaking. Your voice is breaking. Yes.
Just a second. Just a second, ma'am. I'm
Hello.
Yeah. Should I start?
Yeah, definitely you're audible. Just a minute. I'm just trying to get the host. Hello, Shumi. Have you joined back?
Hello. Am I audible now?
Yeah. Yes, you are. It's echoing. You are
Sorry for
using
that.
two, three devices or what?
Yes, ma'am. Using my tab earlier. I think it's. I don't know the. I have some network issues here.
Now you are audible. Please go ahead.
Uh, I hope I'm.
Start from beginning.
So I shall.
Actually,
Okay,
it's
okay.
fine. The introduction
So
is fine. I'll introduce myself. It's fine.
Sorry.
I'll introduce myself when I start
Okay.
presenting.
Okay. Okay. Then it's fine. So you invite Sir and Sir will introduce
oh,
himself.
so it's an absolute
Okay.
pleasure to introduce our next speaker, Professor Himanshu S. The stage is all yours, sir.
Yeah. So thank you, Dr. Bhattacharya, for the introduction. I'll proceed further. So I'm switching off my video so that and this- okay. So what I'll be doing actually, I tried my best. So I asked Professor Ratri, I should thank her for the invitation. So I asked the Professor Ratri, and she said there are a lot of means diverse people are from diverse field. So I'll try to start from the textbook examples what we learned from 10th, 12th. Then slowly proceed to the research. So the topic of my this short term teaching or one hour of teaching or lecture will be quantum mechanical methods to investigate non-covalent interactions in proteins. So I am Himanshu Biswal. I belong to call some institute called National Institute of Science Education and Research, Niger, and we also belong to another big institute called the Homi Bhabha National Institute. We come under this is deemed to be university, so we come under that. So HBNI, we come under HBNI. So I'll tell little more about our institute. There are a bit confusion. I don't know whether you know it or not. People compare IIT and NIT and compare IJR and Niger. It's not true. So IIT and NIT they belong to same minister. I mean administration, and our actually there are two different ministry which conduct this one the Niger and Niger. Niger belongs to Department of Atomic Energy, and there are so many institutes which belong to Department of Atomic Energy, including BRC, TIFR, HBNI, HRI, TMC, many. So we belong to those organization. And this is the National Institute, our institute, Niger, National Institute of Science Education and Research is unique. So I want to tell this one to the lecturers who are present here. They can tell their student about Niger and what we do different than others. So this one is a very young institute which was established in 2007, and this is the first institute to under DAE which has actually UG undergraduate program. So we have 8 schools offering integrated MSc, integrated MSc PhD and PhD. And the basic schools we have like a School of Chemical Sciences, Biological, Mathematics, Physics, then Computer Science, and Planetary Science, Medical Physics. So there are many. We have 8 schools offering integrated MSc, PhD, and PhD. Few of them they will start the integrated MSc soon, but most of the school, actually the basic science schools, have all these 3 programs. This is briefly about our institute, and as I said, I am a professor in school in chemistry. So, but I work a little different than the usual chemistry people do. So I build my setup, experimental setup. Okay, so I did my PhD from TIFR, where we have a huge workshop, and they encourage to have the instrumentation. So I do both the theory and experiment, and I do theory to support our experiment. Again, when we have some experimental data, actually we use those experimental data to benchmark the theory. So today I'll talk the first part, the theory we do to support our experiment. So on fourth, I'll tell actually how our experiment is useful to benchmark the theory. So as I said, I'll talk about something called non-covalent interaction. This is not very new for any all of you, but there are many unknown to be discovered. That's what I'll tell. And as you can see, we look at many different aspects of non-covalent interactions, and there are applications in drug design, in chiral transport, and this stuff to study experimentally. There are not many commercial instruments available, so we built our instrument that I'll talk. I'll briefly show that today and explain more in detail in on fourth. So this is one of the setup. You just remember, it will be helpful for me to describe in on fourth. The supersonic jet spectroscopy, I'll explain what it does actually. Briefly, I'll tell. With this setup, we can achieve 10 Kelvin. We can do the experiment of like it dimer. We have mass selectivity. We have mass selective IR spectroscopy. We can have mass selective UV spectroscopy. We can do the imaging, many stuff. Okay. So then we don't use cryostat for this one to bring the temperature 10 Kelvin. We use some other technique that I'll explain on fourth. So this is called the supersonic jet spectroscopy, what we did in our institute. This is one of the unique setup in India. So we have also recently we are establishing called the matrix isolated vibrational circular dichroism. Here we use the cryostat actually, and uh, this one we can achieve up to 4 Kelvin using the cryostat. Okay, so this one I'll explain again. So recently we went to something called the polarity chemistry, which is a very young actually topic, or a very recently people have started using this stuff, polarity stuff in chemistry, and these are many interesting aspects of that, and I'll talk about the experiment. So do you have I'll request, if you have any questions, please interrupt me. I'll be very happy to answer those questions before proceeding further. So since it is 1.5 hours, I have sufficient time to pay attention to your questions. I'll try to answer all of them. Okay, so please do not hesitate to ask any question in between. Okay, so what I'll do, something called the non-covalent interaction actually. So if you ask the name itself, it says non-covalent, which are not covalent actually, or ionic or anything. So these are non-covalent interactions. And if you ask somebody in chemistry or biology, they call it intermolecular forces. So we'll start with what is called the intermolecular forces or non-covalent interaction. So these are few physical changes or physical stuff you can visualize, and that happens actually because of intermolecular forces. I'll give you a few examples. So what happens when noble gases liquefy? So if you have a liquid helium, what happens actually? So there is something happens between two atoms of helium, and that is we call the intermolecular forces. What property of liquids allow some insects to walk on the surface of water without sinking, right? So there is some forces also exist, and we have observed that, and sometimes we thought actually to give an explanation, but there are many things actually to explain to explain the observations. This is again, there are some chemicals on the leg of the insect and water, there is interaction, intramolecular interaction that allows for the insect to work on that. Why can gasoline dissolve many organic compounds that water cannot? Okay, that is also a simple example. What accounts for the unusual high boiling point of ammonia compared to the like ammonia is NH3, pH3 or anything, AS3 like that. Okay. So what is the primary factor that determines whether a given hydrocarbon will be solid, liquid or gas at a specific temperature? If you take hexane, hexane is a solution, okay? N-hexane or something, sorry, it's a liquid. So if we use as a solvent in many organic reactions, if you take a methane, it is a gas, okay? So there is something is going on, okay, in between the molecules, then it gives rise to some chemical and physical property of the whole molecular system. What forces enable certain small molecules to bind specifically to the active sites on large protein and enzymes? Why, when we design a drug and that drug specifically go to the active site, okay, and like this COVID, right? The COVID stuff, people have drugs which goes to the active site of the protein and block all the activities. Why DNA looks so like a spiral ladder? Okay? So there are many examples. I'm telling some of the interesting example which you can think of. What fundamental interactions allow gecko means a lizard actually, big lizards to cling to walls and ceilings using their foot pads, even without sticky secretions. Okay, without any secretion or any glue, they can work on the glasses also. Why is butter solid at room temperature while olive oil is liquid? Okay, that is also interesting. These are very tense. That's what I told. These are very tense or 11th standard questions which we ask actually to the students. Why does it take significantly more energy to boil water at 100 degrees centigrade compared to methane? That is the simplest question, even though water is much smaller molecule. Why is rubbing alcohol or isopropanol a much better solvent for grease and oil than water? Why does water form spherical droplets on a waxy surface instead of spreading out evenly? These are the few stuff I've given for which the answer is, the answer lie, it is called the intermolecular forces. The intermolecular forces are responsible for this type of phenomenon what we observe in our day-to-day life. Okay. So I'll take a talk about how quantum mechanics helps actually to understand those intermolecular forces and what are the parameters we use. So I try to avoid the equations as much as possible, the Hamiltonian, all the stuff. So to give you a very qualitative picture. Okay. Okay. Is there any questions to ask? I'll proceed further. Am I audible?
Yes, sir.
Hello? Okay. So what are the types of intermolecular forces? These are the mostly these 5 types we consider called the ion dipole interaction, ion induced dipole interaction, dipole induced dipole interactions, dipole interactions, London forces, or a dispersion. Okay. So as a chemist, actually we follow the periodic table, and everything which is listed as non-covalent interaction, these are nothing. These are intramolecular or intramolecular forces, and we name it actually. For us, it is very easier to remember. And if you ask somebody from a physics background or something else, they'll tell these 5 forces. But if you ask a chemist, they'll tell the name: hydrogen bonding, carbon bonding, nitrogen bonding, chalcogen bonding, halogen and erogen bonding. So we name it like our name reactions. We name it, but to remember easily, to explain it in a simpler way. But these all of them comes under these categories. So what is ion dipole interactions? Okay, so you have ion, assuming that, so if I put sodium chloride in water, the table salt, so it dissolves in water, right? What happens? There is a solvation, the chloride ion actually interacts with water. You have a Cl minus, that is called the hydration of cations and anions. The Cl minus interact with the OH actually, OH of this water molecule, whereas the sodium interacts with the oxygen. Okay, So this occurs, as I said, this occurs between, I'll share these slides also. This occurs between an ion, its charged atom or molecule, and a polar molecule, a molecule with a permanent positive or negative end, that is called the polar molecule. And the ions actually, if they are not similar, they are opposite character, like a positive ion attracts the negative one, and oppositely charged, they attract each other. This is an attractive force. This is called the ion dipole. You should have an ion, you should have a dipole for the interaction to happen. And this happens actually most of the hydrogen bonding, most of the hydrogen bonding cases, this is driven by the ion dipole or dipole-dipole interaction. So here, another one, the next category is called the ion dipole induced interactions. So this is the one of the example. You take the nonpolar iodine dissolves in polar ethanol. Okay, why is it so? Iodine is nonpolar, and ethanol is polar. Polar means the OH group is polar, and this is happens actually in presence of the polar group. The unpolar develop the dipole moment or develop the charge separation between them, and that is called the induced dipole. And you have already an ion or a dipole that interacts and gives rise to some intermolecular forces. So this is how the electric field of the ion temporarily distorts the electron cloud of the nonpolar molecule, creating a temporary induced. Actually, if you look at here, creating a temporarily induced dipole, and you have a positive and a negative part of the molecule come closer, and they interact and form some complexes or solvations, and this is how iodine dissolves in ethanol. So the next one is called the dipole-dipole interaction or keystone forces, and this happens between the two polar molecules. If you have two polar molecules, this one. Okay, this is also, if you take a HCl, two HCl dimer actually. So you have a H plus in one end, Cl minus the other end, and you have a dimer. Actually, the first hydrogen bonded stop was reported for a hydrogen fluoride tetramer. It rearranges in a square way, the square manner, and it comes there is interaction between the H plus of hydrogen fluoride and the F minus, actually partial F minus of the fluorine. So these are stronger also, and but weaker than the ion dipole or even if a very strong hydrogen bond. So this one is called the London dispersion forces. If you look at what I said, the helium, right? When you liquefy the helium, bring many helium molecules close together or argon molecules close together. So there are report actually. Yesterday, sorry, on 4th, I'll show you there are argon dimer experimentally determined, and argon, two molecules of argon coming close together, and they forms a dimer, and that mostly happens because of the dispersion forces. And under dispersion, it is also called as induced dipole and induced dipole interaction. You can see the right hand animation. When you have a very isotropically distributed electron density, when they come closer, there is an anisotropy between the electron density. Some part of them will have more density, some will be deficient, and when you have a more electron density, it will be negatively charged, and the other one will be positive charged, and they will attract each other. That is called the dispersion. Okay, fine till now. It is fine. I'll go to the non-covalent interaction in detail. Is it fine, this one? Should I proceed further? Okay. So this is called the non-covalent interaction. It can be attractive, and sometimes you call the repulsive is very, and most of the time you use the term attractive. You have a donor. Okay, so D stands for the donor, X stands for the acceptor. The donor will be electron deficient, electron rich, acceptor will be electron rich. Okay. So I write NCI. So if you look at this called hydrogen bonding, you have a group for group 1. Group 1 means the hydrogen belongs to the periodic table. Group 1 was the periodic table, and this dotted line represents the hydrogen bond. These are the neutral molecules, If you look at the overall charge of water will be 0, the overall charge of other water will be 0, but they have a dipole. Okay, so you have a dipole and you have a ion. Actually, if you look at not ion, you have electron rich species, the oxygen. Then there is interaction through this dotted line, and this is called hydrogen bond. The other one is called the carbon bond and or tetrale bond. TT stands for the tetrale. The carbon group is called carbon, silicon, germanium. That group is called the tetrale group, and this is called tetrale bond. This is one of the example here. The oxygen electron actually, this is the electron rich, and this carbon is a little electron deficient, and they interact and forms a supramolecular structure. So we can have a nitrogen bonding. So nitrogen is a nitrogen group is called the nitrogen. Nitrogen phosphorus. Here the oxygen is going to the phosphorus. Bonding orbitals. We can have a chalcogen bonding, which is the sulfur selenium. Actually, the lone pair of electron actually goes to the antibonding orbital of this molecule. So this is sulfur, and some other atom will be there. That is called the chalcogen bonding, and this is called the halogen bonding. Then this is going to the bromine. All of these are the halogen bonding. As I said, all these bondings we can categorize in 5 types, but we remember as a chemist we remember in this way. So the next one I'll tell actually how do we establish what quantum mechanical stuff we use or the theory we use to establish there is interaction. Okay, so there is the dotted line stands for the interactions. What are the methods we use to convince or to tell that or confirm that there is an interaction between these two molecules. So if you are really interested, recently we have a review. So this review talks about if you have had of hydrogen bonding and pi-pi stacking. This review talks about the different type of interactions in biomolecules and how it helps actually for the drug, for the enzymatic activity, many other stuff. Okay, you can go through this one. So as I said, the hydrogen bonding, there are many examples. This is not new for any of you, but there are, at the end you will realize there are many things to be explored. So this is almost more than 100. Many stops many stops are there to be experimentally verified, and there are many controversial issues that are going on. Where I did my PhD, and many of my students did also PhD on hydrogen bonding only. Okay. So there are many things. It's not the concept is established, but there are many new things that are coming up day by day. As I showed that I will not go through this one. So the consequence of hydrogen bonding, you know, the high and low melting point, the solubility, viscosity. If you look at H2O is a liquid while H2S hydrogen sulfide is a gas, and they say sulfur forms weaker hydrogen bond, which actually it is true for H2S, but not for all the sulfur compounds that we have proved recently using both experimental and theory. And solubility also, you look at low alcohol results in water, viscosity and surface tensions also governed by the hydrogen bonding, low water congestion with water in case of solid-ice hydrogen bonding causes case-like formation. So these are stuff we explain, right? Why ice floats on the liquid water, we can explain using this hydrogen bonding concept. As I said, this concept is more than 100 years old, but you can see number of papers are coming up, and number of publications, number of books are coming up. So we have a contribution in 2015 called the noncovalent forces. Here we talk about the hydrogen bonding with sulfur and selenium, non-electronegative atoms. As I said again, I am showing this one. You can look at many type of, you might have had, that is called sodium bonding, trial bonding, tetrale bonding, nitrogen bonding. So you might have heard of hydrogen bonding or halogen bonding. These are the new stuff which were discovered in last 10, 12 years. And this has lot of importance. If you are a computational chemist or biologist, structural biologist, please Please remember, these interactions has a huge role to determine the structure, to design the drugs, many things. So as I said, how do we identify these are the interactions? Okay, so we call it a donor acceptor orbitals in non-covalent interaction. If you look at hydrogen bonding, the lone pair of the oxygen, if you take water, there are two lone pairs. One lone pair of the oxygen, lone pair of electrons of this one goes to the antibonding orbital of a OH bond. This is the antibonding sigma orbital of OH bond. This is how the hydrogen bonding is established. Here the lone pair goes to the antibonding orbital of a CH when the carbon is involved. So the first atom involved in this interaction, the nomenclature is like that. This is my donor molecule, this is my acceptor, this is called the carbon bonding. So nitrogen, again you look at the first atom is a nitrogen atom, that's why we call the nitrogen bonding. This is the chalcogen bonding, then halogen, the iodine is involved, and all of them is going to the sigma star orbital, the antibonding orbital. So then this is called the aerogen bonding. Okay, but even if it is this is XCO, xenon oxychloride, and the lone pair goes to the xenon and oxygen bond. Okay, antibonding this. So whatever I showed this one in this slide, actually all of the electrons are going to the antibonding orbitals of this bond, and that actually call another language we use, another term we use for this one. This is called the sigma hole. So this is arises on sigma hole are the electron deficient regions resulting from the anisotropic electron distribution in molecules. So look at this one. So this is one of the example I'm telling. The CH bond formation. You have a carbon. You unpaired electron of carbon here and unpaired electron of this one. It forms a covalent bond. Okay. If you look at this one, okay, I have taken CF4, CF3Cl, CF3Br, CF3I. Okay, so the difference between here I have a fluorine atom, all the fluorines are there, so it is isotropically distributed. If you go on substituting the fluorine with chlorine, bromine, and iodine, so iodine is more polarizable. Okay, so what will happen actually? The iodine has more electronegative and positive. Opposite to that, you will have a electronegative region. Okay, so because of this is we call it a sigma hole, and this is responsible. If you have a lone pair of electron, it will interact with this positive part of this one. Coming back to the fluorine, you have a negative here. Okay, so this red stands for the negative. Then as I go on substituting chlorine, bromine, so iodine has a positive part and it can form halogen bond quickly than this one. And this region we call the sigma hole. So the non-covalent interaction, whatever I showed, could be the lone pair or of the electrons. There is possible of non-covalent interactions with the pi electrons, like the benzene or the stuff, like the SH pi hydrogen bonding or OH pi. Then the cation pi interactions, where the electron goes from the pi orbitals to the ion or the molecule. As electron acceptor, you can have n pi star interaction. That is another type of interaction, which is you will find many of this interaction in polyfluorine structures. These are responsible for the folded structure of the polyfluorine, and that is called the n pi star interaction. Anion pi interaction is also possible, where the electron comes from the chlorine to the antibonding pi orbitals. Okay, here the bonding pi electrons goes to the antibonding orbitals of the SH bond. Okay, so this is a pi orbitals as electron acceptor, pi orbitals as electron donor. So there are other categories of non-covalent interactions. Now come to how to establish or confirm hydrogen bonding, or in particular, and non-covalent in general. So what we do the experiment like the quantum mechanical calculation, or theoretically if you look at, we find it out the electron density, donor acceptor orbital overlap, then the higher stretching frequencies, all other stuff we do. So I'll tell the computational part or quantum calculations, how we use them to find it out, those interactions. Okay. So first, how do we confirm? Let's say I have a monomer, I have another monomer A and B, then it forms a complex. Okay, whether there is interaction or not, positive or attractive interaction or not, what we do? Find it out to the binding energy. Okay. So this binding, if there is an interaction, the energy of AB will be less than the energy of summation of energy of A and B individually. And then you can the difference between these energies we call the binding energy. So here it comes to the computational part. So the binding energy is not sufficient to tell. Actually, we have to do some corrections, and that is called the basis set superposition corrections. Okay. So I wrote in terms of binding energy, that is just a difference in energy of dimer and the respective monomer. Then we call the interaction energy, which is actually has many corrections, called the binding energy, then the relaxation energy, then the basis set superposition energy, then the 0 point energy. Why do we need 0 point energy? Experimentally, actually, we cannot go to the bottom of this potential well. We measure actually everything. More, all the molecules will be in the p is equal to 0 state at least, or more than that. So we have to take account of the 0 point energy. So what is the del E, the relaxation energy or fragment relaxation energy? So here the alpha and beta stands for the basis set used. Okay, when we do a calculation, we use a basis set. Okay. Alpha stands for the basis set of monomer A, beta stands the basis set of the monomer B. So what we do actually, this relaxation energy, we have to do the correction. So the energy of A in B minus the energy of A isolated A, okay, is the how the monomer is relaxed actually gain or loses the energy in the dimer, that is called the relaxation energy. Similarly for the B. So we need to correct that. Then something called the basis set superposition error. So that is actually, this is very crucial. Those values are very less, the relaxation. Sometimes we avoid, most of the times we avoid, but basis set error, superposition error, we cannot avoid. So what it does actually, so if you take a monomer, if you take a dimer, okay. So let's say I have a water, and a hydrogen fluoride dimer. Water as a monomer, I have a 3 atom. So if I take a 2 basis set for each atom, I'll have a 6 basis set. So if I hydrogen fluoride 2, another 10. So if I take only H2O and optimize this one, find it out the energy, I have 6 basis set. But in case of a dimer, when I'm optimizing A, so you have a basis set, actually you have 10 basis set. So that is called when you have a basis set, the energy will be defined, and the difference actually we have to take into account, that is called the basis set error. Okay. So here it gives E alpha ABA, that means the energy of A in the dimer AB with the basis set alpha, okay, minus the energy of A in the dimer AB with the basis set, with the whole basis set. Alpha union beta means the whole basis set. Okay, this is how it is. It needs to be corrected. So as I said, so interaction energy is one of the parameter which will tell actually there is a non-covalent interaction or not. Okay, so this is one of the parameter. If I have a negative interaction energy, then I can tell there is attractive force. After correcting all of them, unless until you correct, then it will be misleading. The negative can be positive, and you might be thinking this is the dimer, and that happens if you look at the argon dimers, all the stuff. So if you don't correct it, you will never have a. It will be misleading actually. So you need to have these corrections. So is there any explanation to be explained, or any doubts? I need a response to proceed further. Anybody? Am I audible? Hello?
Yes, sir.
Yes, sir.
Okay. So next one. Here I am showing. So first of all, we look at the structure which I didn't tell. So we look at this example I'll follow. Okay. So I have a pyridine which forms a halogen bonded complex with this CF3I. Okay. First of all, what we look at the distance between these two, this nitrogen and iodine. So the distance that is called the structural criteria. The distance between these two will be smaller. Actually, the summation of the van der Waals radii of nitrogen and iodine. So the van der Waals radius of nitrogen is 1.55 angstrom, and iodine is about 2 angstrom. If you add them, it is 3.5 angstrom. Okay, but when we optimized or we looked at in the database, you will find many actually which is less than 3.5 angstrom. That gives us an idea actually they come closer. That means there is some attractive interaction. That is the structural parameter to find it out the non-covalent interaction. So this plot, the plot B, shows actually the density plot actually. So here the D which stands for with respect to, this is normalized with respect to the van der Waals summation of van der Waals radii of iodine and nitrogen. And if you look at, if it is less than 1, that means some interaction, and we'll find the complexes we sought in the crystal structure database. We found many actually, many of them forms this complex. The structural information is the first hand information to establish whether there is non-covalent interaction. Then we find it out the energetics. As I said, we take the monomer energy, then the dimer energy, and subtract that. We find it out the interaction energy. Then we do all the corrections. If you correct the 0 point energy, that is called the D0, which actually experimentally determined. Then the equilibrium, the energy at the equilibrium, the monomer and the dimer. So this is how. If you have a negative value, then it is attractive and there is non-covalent interaction. As I said, then you can decompose those. There are schemes, many schemes to decompose the energy. You can find it out whether the electrostatic or dispersion or induced, many things. The 5 different way of energy decomposition we can do. So the next, the structural, there is structural parameters you can use. There is energetics parameters. Then another stuff we call the natural bond orbital analysis. What it does actually, it treat the monomer and monomers and dimers individually. So if you have a monomer, this is the nucleophile, my pyridine. You have a lone pair of electron here. Then the sigma star orbital of a Ci bond, which has more energy. When they come closer to each other, there is interaction between these two, and you can use the Hamiltonian. It is the second order perturbation theory you can use, and then you can find it out the orbital interaction between these two. If there is orbital interaction, you can find it out. This energy will be low. The lower energy from one of the lowest energy of a donor or acceptor will tell about the total orbital interaction energy. So this is we call the natural NBO analysis, natural bond orbital, and a donor acceptor orbital interaction. This is one of the criteria to identify whether there is non-covalent interaction or not. Then what we look at actually, that is the sigma hole information. We look at the molecular electrostatic potential. If you look at the first term, represents the potential due to the positively charged atomic nuclei. Here I have a positively charged atomic nuclei, any of them. It's a summation because there is a multiple nuclei in the molecule. The second term represents, this is the second term, represents the potential due to the negatively charged electron cloud. This is an integral because the electron density is continuous over space. The equation essentially, what it does actually, it calculates the electrostatic interaction that a tiny or hypothetical positive test charge would experience at each point R around the molecule. So what does it mean? If I look at the pyridine, if I put a tiny positive charge, okay, so what is the electrostatic interaction energy for the tiny positive charge due to the electron will give me all the interaction potential. If I place the tiny positive charge, that will give you information about the molecular electrostatic potential. So this is the equation we use. There are many software available. You can write your own code also to find it out, this one. And here this is the convention we use. Red indicates the region of most or negative electrostatic potential, the electron this one. Then the blue one represents the positive electrostatic potential, and the green is almost zero, the neutral. Okay. So since if you look at the pyridine has a nitrogen is electronegative. So it has a electron density, more electron density, so that the molecular electrostatic potential is more. Where iodine in CF3, in iodine you have a positive electrostatic potential, because iodine is less electronegative than the fluorine. So you have a positive electrostatic potential in front of the iodine. So this is one of the stuff actually to tell whether if you have two monomers, one should have a positive electrostatic potential, the other should have a negative electrostatic potential. The interacting atoms actually involved, then only there is a possibility of an interaction between these two. So this is one way quantum mechanical calculations we perform to find it out whether there is interaction possible or not. So this one is more interesting, that is called the topology of electron density, quantum theory of atoms in molecules. So this one I have taken from this monograph, the quantum theory of atoms in molecule by Russell, Matt and Boyd. So this one, this molecule is called morphine molecule. Look at the molecule here. Okay, so you have a lot of covalent bond. You have this dotted line stands for the non-covalent bond. Okay, so what it does actually, it looks at the topology of electron density. Topology next a few slides I'll explain what is the topology. It looks at whether the electron density is maximum or minimum, how the maximum or minimum looks like. So if you have a non-covalent bond or a covalent bond, that is, you should have a maximum electron density in all the directions, but there will be only one direction, while there will be the minimum electron density, or one point if I identify, that point is called the bond critical point. I'll explain that one in the later slides. Okay, so this one is very useful to identify the whether it is a covalent bond or non-covalent bond, whether there is a ring or there is cage. So the electron density topology will tell. Okay. Yeah. So this one I'll spend a few minutes on this one. Topology of electron density, quantum theory of atoms in molecules. So what we find it out to something called the critical points in electron density. What is the critical point? Okay. So you will have a okay. So the critical point in the electron density is a point where the gradient of electron density is zero. Okay, del rho is equal to zero. And if you look at how do we find it out, there are nomenclature. The Hessian matrix of actually the second derivative of the electron density in x, y, z. If you look at the second derivative, you have a second derivative with respect to x. You have a derivative with respect to y and x. If you look at the entry of this matrix, okay, all the entries, if you have the second derivative in the x, y, z coordinates. This is called the Hessian, right? So if you have done all this, this is the Hessian of matrix of electron density. Then what we do actually, we diagonalize, okay, to have the diagonal components, and these are if I diagonalize, this one will be the eigenvalues. These are called the lambda 1, lambda 2, lambda 3. Okay, and at a critical points, the Hessian matrix is diagonalized to obtain 3 eigenvalues and their corresponding eigenvectors, which we use actually to find it out the bond path. These eigenvalues represent the curvature of the electron density along the 3 orthogonal principal axes, okay, x, y, and z axis. So I need this lambda 1, lambda 2, lambda 3 to tell actually about the bonding nature. Okay. So the classification of critical points, right? So first in the last slide I said if you take the gradient of electron density is equal to 0, then you in the Hessian matrix actually you can diagonalize. You can have 3 components, diagonal components, and these are the eigenvalues of the second derivative of the electron density. And depending on the nature of those eigenvalues, actually nature means whether it is positive or negative, we can define these critical points. So the critical points are classified by an ordered pair called the rank and the signature. The number of non-zero eigenvalue for a topological stable critical points in 3D R is always 3. We will have a 3 non-zero eigenvalues. Sigma is the signature. For our stuff, all the diagonal elements, we assume these are non-zero. And what we do in chemical bonding, that will be also possibility. One of them could be 0. So we will not go detail about the mathematical part, or I am not expert actually to tell more about that. So then we look at the signature, that is the rank, non-zero eigenvalues. Then the signature, the algebraic sum of the signs of the eigenvalues, number of positive eigenvalues minus the number of negative eigenvalues. That will tell you the signature. So as I said, I have 3 diagonal elements, 3 diagonal values, and none of them will be 0. So my rank will be 3. Okay, non-zero eigenvalues. So 3 non-zero eigenvalues. Always in our case, the rank is 3. Then the signature. The signature could be, I can have 3 of them positive, I can have 3 of them negative, I can have 1 of them negative or 1 of them positive. So depending on such situations, I can have a 3 minus 1 critical point. What does it mean? I have the eigenvalues of the Hessian matrix are non-zero, all the eigenvalues, and 2 negative eigenvalues. Okay, so lambda 1 is less than 0, lambda 2 is less than 0, lambda 3 is greater than 0. So this minus 1 stands for that. So I have 1 minus 2 negative, so that is minus 1. So this one, what it signifies, physically what it signifies, it is a saddle point in the electron density. It is a minimum along the bond path, the line connecting, I'll explain it, and a maximum in any perpendicular directions. Okay. So if you look at, this is one of the molecule called cubane. Okay. So you have a red dot, you have a green dot, you have a yellow dot. Okay. So this red dot is called the bond critical point. What it says, it is a minimum along the bond path. Okay, so you have a electron density at this point, you have a minimum, and if you consider this bond path, okay, and everywhere perpendicular to this bond path, okay, will be maximum. Okay, so we will have a one minimum and a many maximum. That's what this is called the bond critical path. The existence of BCP and bond with chemical bond, so it is used in many non-covalent interactions. So next one is called the ring critical point. Okay, so ring critical point, what you have actually, you have the lambda 1 negative and 2 positive eigenvalues. So 2 minus 1 will be plus 1. So what it says, it is again a saddle point in the electron density. This is minimum in the plane of the ring. Okay, in the plane of the ring, this is the ring critical point, and maximum perpendicular to the ring. Okay. So this one, if you have a 3 plus 1 critical point, then you can see actually. So if I have a water, if I have a benzene, so water will have a bond critical point, where the benzene will have a bond critical point for the CC bond or CH bond, and in addition to that, you will have a ring critical point. Okay, that will give you information about whether you have a ring structure or not, or closed structure or not. Then you have a cage critical point. Okay. So this is 3 plus 3, all the eigenvalues are positive, and this is found to center of a cage of atoms. If you have a ring here, you have another ring. So it is a cubane structure. Okay. So this is called the cage. The center one is called the cage critical point. In all the surfaces, you will have a ring critical point, but as the center, you have a cage critical point. So the other one, when you have all of them will be negative, that is called the negative eigenvalues, that is the local maximum, and this is the nuclear positions. That is called the nuclear critical point. It gives the nuclear positions. Okay, so we actually in chemistry we need 3 critical points. Carefully look at the bond critical points will tell about the bond. The ring critical point will tell about whether there is a ring structure or not. Cage critical point will tell about whether there are many rings combined together to form the structure. These are really helpful for us to tell whether there is a covalent, non-covalent, or ring or planar molecules. So again, I am telling this example, as I said, I am taking this example. If you take the pyridine and this is CF3I, so we did the calculation called atoms in molecules. You can see there is an interaction. These are not covalent bond, okay? So there is an interaction between these two. You can have a ring critical, sorry, bond critical point along this vector, the nitrogen and iodine, and that gives us idea there is a non-covalent interactions possible, okay? Okay, so there are many stuff. Then we look at not only the electron density, the Laplacian of the electron density, the energy density, the many stuff. We look at it to tell about whether there is an interaction between these two or not. And there are also, depending on the magnitude of the electron density, you can identify whether there is a very weak interaction, there is a very strong interaction, there is a covalent limit or a non-covalent limit. Okay, this is a very nice paper. You can find it out many. So this is really helpful for us to identify whether there is interaction. Again, to quantify whether the interaction is weaker or stronger. So there are many stuff is developed also. This is again exactly same. It is used the quantum theory of atoms and molecules. And what this one gives a very beautiful picture in the three-dimensional picture, where you can have the isosurfaces, and it takes actually reduced density gradient instead of the density. So just for multiply second eigenvalue of the electron density lambda 2 with this one. Actually, if you look at sign of lambda 2, sign means it could be positive or negative, then the electron density, okay? And the construct the isosurfaces, this is a three-dimensional. The other one was a two-dimensional picturization of the electron density. This is a three-dimension, and it takes a care of, if we add say lambda 2, actually it gives idea whether there is non-covalent interactions, van der Waals interactions, or steric repulsion. It gives many idea. So this one we have taken actually for this our molecule the example. So if it is a blue, that will be a very strong non-covalent interaction. It is, could be hydrogen bond, strong dipole-dipole interaction, or could be halogen bond. If it is green, then the interaction will be weak interaction, like the van der Waals interaction. If you take argon dimer, this is at the van der Waals or dispersion dominated, and this color will be very greeny. Okay, not all. This is a bluish color. This color will be green. If it is red like this ring one, this one will be repulsive, actually the steric repulsion because of the carbon. So a little steric repulsion gives all the ideas. Not only the attractive, it gives the idea about attractive interaction. It also tells about whether strong or weak or repulsive or attractive. I'll summarize whatever I did actually using the quantum mechanical. First, we looked at the structure, looked at the van der Waals radii, then it gives us information about whether they are bonded or not. Then we looked at the interaction energy. We have to be very careful to tell about the interaction energy after the correction only. The BSCC, relaxation, zero point energy, all the correction you have to consider to tell whether it is bonded or not. Then you can look at the donor acceptor interaction energy and tell it further. You can use the molecular electrostatic potential whether to see whether there is a positive electrostatic potential or negative electrostatic potential. And then you can look at the bond critical point, then the reduced to electron density gradient, many stuff. Okay, so you can find it out using this tool. You can tell whether there is non-covalent interaction exists or not. So is it clear to any all of you? Am I audible? I cannot see you. Am I audible?
Yes,
Yes,
sir.
sir.
Do
Yes,
you have
sir.
any doubts till now? Do you have any doubts? Any
Yes,
clarifications?
audible.
Any clarifications? Hello. Okay, I'll go to the next slides. Any?
Yes.
Okay, so I tell about why these are important. Why should we do? Coming to the proteins. So this is a very you can see this paper is published in Science 10 years ago. This is called the possible implications of carbon bonding in photobiology. I will tell why the carbon bonding. Knowing the basic concept is very important. So this paper says actually, so they were doing a ultrafast spectroscopy. They dissociate the carbonyl molecule which is bind to the protein actually ligand dissociation, and they used huge laser energy. The CO molecule dissociates. The rest of the energy actually dissipated through multiple interaction to one moiety to the other. Okay, so what is, if you look at, they are dissociating here, okay, but they are getting the effect in this one which is far away from each other, and they are telling in this science paper, they told this one is because of the multiple hydrogen bond. Okay, so it is not raw. If you look at the multiple hydrogen bonding, this will not go, the energy will not reach this point, okay, to have a perturbation in the CD corner. So for that, there is something irresponsible we look at, and this is, I'll tell actually, we call this is carbon bonding, and this is a new concept and which can be useful. And this carbon bonding actually is discovered by Professor Arunan from IIC, and there are many one. As I said in the previous one, the carbon bonding, the oxygen lone pair goes to the sigma star orbital of carbon, linked with some other negative atoms, and there are many controversies are there. Okay, well, I don't have time. I'll still explain this one. So look at, so what I summarize this one. So I looked at many paper very recently published. So in the NMR, they says if you have a carbon bonding, these are the experimental stuff. You will have a downfield shift, and you can tell. But there is a big paper from JAX in 2018, in 3 years after this one, and they say it should be shielding, and you have a upfield shift. There is a gas phase NMR actually, solid state NMR, solution NMR, gas phase. These are experimentally. Gas phase NMR is computational, and it says it should be deshielded. Okay, but the deshielding is much more, 20, almost 10 times more than the experimentally observed. Whereas the solution one says it is the no, other way, it will be shielded. The carbon actually which is interacting will be shielded. So this actually gives us a lot of problem. We thought, why is it so? Which is whether the experiment is correct or the theory is correct. Whether you are going to believe this Journal of Physical Hardcore Physical Chemistry paper, or a very high impact journal called the Journal of American Chemical Society. Whether you are going to believe the solid state or solution or gas phase. This was really puzzling. Then we thought of writing our code to look at whether those interactions are there in proteins or not. We looked at a such course in protein. We wrote this one in Python, and we found it out too. There are many such interactions are there in proteins, and you can find there are many huge interactions in there, and it is available in all the protein structure, all the secondary structure of the proteins. And then we try to do the, okay, these are whatever methods I told you. Are it is molecular electrostatic potential, this is the reduced to gradient plot, this is the atoms in molecule, this is the donor acceptor interaction energy. These are the protein structure we have taken from the PDB data bank, and you can see that a huge such interaction exists in proteins. Okay, but to justify our which one is correct, I showed these three papers, which one is correct. We try to do many experiments actually, but unfortunately we none of them actually, our experiment didn't match with none of them. Still the data is pending, we could not communicate. Okay, so we did both the theory and experiment, and to find it out to this interesting result. We did a lot of, then we thought of to change this one to look at another system. And I look at here, here I have oxygen, it interacts with the carbon actually, here we call it carbon bonding. We thought in that way, and they performed many experiments And again, there is a shift actually, NMR shift, but we didn't find it the carbon bonding. Instead, actually, what we found actually, this is called the N-pi star interaction. Okay, so this one we still we are not confirmed whether because of the carbon bonding there will be desilting or silting in the NMR spectroscopy. There is no experimental evidence still now. And this is the first experimental evidence of N-pi star interaction in solution, and this was published in chemical science. Since today I'm talking about the theory, I'm not going detail about the experiment, and maybe on fourth I'll detail about the experiment. And what we observed actually, we took this protein, this one, as I explained in this science paper, they told it is because of the hydrogen bonding, the energy dissipation happens. But what we found, this moiety is actually linked with the center through, not through multiple hydrogen bonds, but through directly a carbon bond. So if you look at, you have a carbonyl, and here you have the CH3 group, they interact with each other, and that could be the region actually, the energy transfer happens from here to here. So since the paper was published in 2015, the concept was not that developed, and the theory was not that developed actually, people to accept it. It could be the carbon bonding. Since the hydrogen bonding was a established concept, and one can explain it through hydrogen bonding. I am telling, this is how the theory helps the experimentalist to explain their data. I'll give few more examples also. And people started using this type of concept in the materials chemistry, material science. I'll tell you another concept actually. This paper again, this was published in 2018, and if you look at, it is by the Professor Francis Arnaldo. So they are looking at the catalysis using this one. They did a mutation, okay, from serine to alanine, and there is found increase in the activity. Okay, so first they did the mutation, uh, okay, the mutation, and they found the catalytic activity, and they could explain because of the pi stacking. When they did the mutation from serine to alanine, there is a difference between serine and alanine. The difference is very small. Serine has a OH group and alanine doesn't have a OH group. Okay, so this mutation gives the increase 2.5, but they don't have any. They didn't any explain. They didn't have any explanation for that. So what we observed actually, so this serine molecule, so serine has a OH. When the serine is there, so what it does actually, it interacts with the product. This is the product of the reaction, and the product doesn't come out from the enzymatic catalytic center. So when you replace this serine with alanine, this interaction is not there, and the product comes out, and it follows the Lee-Chatelier principle, and your turnover number increases. What could be this interaction? This carbon is not an electronegative atom, and this carbon is not a carbene also. This carbon is saturated. It has 4 carbon linked to the 4 carbon atoms. How this interaction is possible? Then we looked at the crystal structure. If you look at this is one of the crystal structure called the propylene. It doesn't. If you look at the crystal structure, actually, the supramolecular structure is because of this interaction only. You have a CH and interact with the carbon. This was our discovery, and we did whatever quantum mechanical methods we used. We did those experiment methods we used. We found actually there is a interaction. You have a interaction actually. This hydrogen, this carbon interacts with the hydrogen. This hydrogen interacts with the carbon. There is a two-way of interaction, and it is actually a resultant of carbon bond and hydrogen bond. We named this one, and the name is we gave it called the carbohydrogen bond. So as I said, we did many. We compared, and this one. Then there are experimental. There are no experimental spectroscopic proof of this type of bonding in the literature, and but there could be. These are computational data. That could be possibilities. Somebody or will verify experimentally. Then after this one, we contacted actually the authors and telling that this is could be because of this interaction, and we wrote actually to them. This could be this interaction we call the carbohydrogen bond, and this is the Nobel laureate. They are really thankful to them. They reply to, thanks for sharing your work. Very glad to see that you used your newly established concept of carbohydrate bond to explain the mutational effect in a. It is very interesting study. So they replied actually, but till now I am telling, I am not confident. This could be, there could be other factors, but it needs experimental to verify. The theory predicted, unless until it will be verified to the experiment, how can we be certain? So it needs both ways. So that's what I kept two talk. One with the theory, the other one will be the experiment. You can have a network actually, like the covalent organic framework, metal organic framework. You can have a network. You can have a supermolecular structure using that concept. Okay. As I said, so those carbon bonding and this one are not experimentally established by spectroscopically. So this is another recent work actually, which is controversial. So the IPAC definition of hydrogen bond, it says X is more electronegative than hydrogen. But recently we observed, if you look at the metal hydride, X is electronegative. Okay, X is hydrogen is electronegative. Okay, not electron positive, but still it can form hydrogen bond. Okay, so those are controversy. Is it possible to have a metal hydride hydrogen bond? Computationally prove it. There are paper we published this one in 2019. This is our group. Then there is a Jack's paper, and they are telling there is other paper. They are complaining with each other. Then another follow up paper came. They are telling how the negative charge can form hydrogen. Always, if you remember, for a hydrogen bonding to happen, the H should be del plus, and whatever we showed in our paper, they told in experimentally they verified the next Jack's paper in 2023. Are not they told this is the experimental proof it. Then another follow-up paper in Jacks it came the hydridic hydrogen bond. The H minus cannot form hydrogen bonds. Then the IPAC definition, and then the who gave the IPAC definition, they came forward and said no, there is some problem is there, but unfortunately none of them cited our paper. This is the first paper, and it was published as a part of the special issue of Young Scientist. So this one, none of them have cited. So till this experimental verification is needed. Why it's so difficult? I'll tell in on four. Why is it so difficult to the experiment to verify it? And these are the spectroscopic signature which we can use in the experiment. These are these are computed. We can use those. So that went actually whether H minus can form hydrogen bond or not. The other one, whether you should have the hydrogen bond forms, so like you have XH, either it could be the Y could be oxygen, sulfur, selenium, fluorine, chlorine. Those are electronegative. Is it possible to form hydrogen bond with the electropositive atoms? So if you look at the polonium is electropositive than any of the hydrogen. Its electronegativity is 2. So whether it is possible to do that, and we experimentally found it is possible. Computationally we predicted it is possible, and it needs actually. Okay, no spectroscopic or any sort of experimental evidence of hydrogen bonding with polonium or metal hydride. What could be the reason? That I will answer on 4. So I thank my PhD and postdoc students, many things, many financial support. So again, thank you all. So we have a very beautiful campus. So if you have some time, please plan to visit us, and I'll be very happy to take a question from you. So don't hesitate to ask. I may not be possible. I am not a hardcore theoretician, but I'll try my best to answer. If I cannot answer, I'll go and read it. Thank you very much for your kind attention. Professor Ratri or
Thank you so much, sir. Thank you so much.
yeah.
On behalf of everyone, I would like to express my sincere gratitude to you for your mechanical methods to investigate non-covalent interactions in proteins. Um, we learned about the concepts of hydrogen bonding, types of intermolecular consequences of molecular forces, then quantum in molecules, hydrogen bonding between and then classification points, implications of carbon bonding in photobiology, carbon hydrogen bond biology, and in material science as well. Thank you